If you're learning Go and want to prepare for real coding interviews, this video is for you. We will solve 15 practical Go challenges with clear inputs, outputs, and explanations so you can understand the pattern behind every solution. We start with slice fundamentals, because many Go interview tasks are really about careful iteration and simple state tracking. In practice, this is how you pick the highest score or largest amount from a list. Let's write a function that returns the maximum number, but also returns an error when the slice is empty. Now we run it with a normal slice and then with an empty slice to check both paths. Let's break down why this works. We start with the first element because it is already a real value from the input. Then every next number gets one chance to replace the current maximum. So the final value is the largest one we saw. Now we show the important habit. Check for an empty slice first. This is the best approach when the function reads nums, because an empty slice would otherwise cause a runtime panic. For practice, try returning the index 2. That makes the task closer to real interview questions, where you often need both the best value and where it was found. Reversing a slice comes up in recent activity lists, undo history and priority changes. Here we mutate the original slice, so we do not create a second one. Now we run it and compare the output before and after the reverse function. Let's break down the algorithm. The left pointer moves forward, the right pointer moves backward, and every swap puts two values into their final positions. When the pointers meet or cross, the slice is fully reversed. Now we show the best way to handle this when mutation is allowed. Swapping in place is simple and memory efficient because it uses the existing backing array of the slice. For practice, test an even length slice. It helps you confirm that the loop condition works for both odd and even numbers of elements. Next, we combine slices with maps, which is a common pattern for filtering and membership checks. Duplicate cleanup is useful before sending user IDs, tags, or codes into the next part of a system. Here we use a map as a set and we append only values we have not seen before. Now we run the code and check that the first order is kept. Let's break down the result. The first Go is added, the first API is added, and later repeats are skipped. Because we append during the original loop, the final slice keeps the same first seen order. Now we show the best set representation in Go, when the map only answers yes or no. Struct is a good value type because it carries no extra data. For practice, add a skipped counter. That small variation makes you track both the clean result and how much duplicate input you removed. Now we use maps for counting, one of the most useful beginner patterns in Go. Frequency counting is the map pattern you will use again and again. We create a map from string to int, then increment the counter for each word. Now we run it and print the keys in a fixed order so the terminal output is predictable. Let's break down the counting. The first time a word appears, its count starts from 0 and becomes 1. Each repeated word just increments the same map entry. Now we show the cleaner Go style. Use counts directly because the 0 value for int already gives us the correct starting point. For practice, count words from a short sentence. If you want a harder version, normalize the words to lowercase before counting. The last challenge in this batch moves into strings, where rune-aware code matters more than byte indexing. This problem is useful for compact codes, simple validators, and interview warm-ups. We solve it in 2 passes. First count each rune, then scan again to find the first count of 1. Now we run it with level up and check the first unique character. Let's break down why V is the answer. In level up, L and E repeat, then V appears once and is the first unique rune in the original order. The second pass is what preserves that original order. Now we show the important string habit in Go. Use range over the string when you mean characters, because byte indexing can break once the input contains non-ASCII text. For practice, return the position 2. That variation forces you to think about whether you need a byte index, a rune index, or both. Now we move into string challenges. These are common in junior interviews because they test whether you can choose the right data structure instead of forcing every problem into loops and sorting. An anagram check is a good place to use a map instead of sorting. First, we reject strings with different lengths. Then we count characters from the first string and subtract characters from the second. Now we run it with listen and silent, then hello and world, and look at the output. Let's break down why this works. Listen and silent use the same letters. So every count returns to 0 and the function returns true. Hello and world do not have the same character counts. So one of the counts goes negative and we return false. Now let's show the better habit to remember. Return early when lengths differ, because there is no need to build a map for impossible matches. Also decide up front whether your real input should ignore case, spaces, punctuation, or accents. For practice, change this solution so it treats spaces and uppercase letters as irrelevant. A good test case is dormitory and dirty room. That variation forces you to add a small normalization step before counting. Next, we use slices like stacks. This pattern is simple, but it shows up constantly in validation problems. Balanced bracket checks are really stack problems. When we see an opening bracket, we push it onto a slice. When we see a closing bracket, we compare it with the last opening bracket, pop it, and then we run the script to verify both examples. Let's break down the result. The first input closes every bracket in the reverse order, so the stack ends empty. The second input tries to close a square bracket while the top of the stack expects a parenthesis, so the function returns false. Now let's show the best structure for this kind of validator. Keep the expected pairs in a map from closing bracket to opening bracket. That makes the check compact, and adding another bracket style later is only one map entry. For your variation, let normal characters pass through without affecting the stack. Then test something that looks closer to real code, like a function call with brackets inside it. This turns the toy example into a more realistic validator. Now we combine structs, slices, and maps. This is the kind of data shaping you do all the time before returning an API response or building a dashboard. Grouping records is a daily backend task. Here we create users with names and roles, then build a map from role to a slice of users. Now we run it and print admin, editor, and viewer groups in a predictable order. Let's unpack the grouping pattern. The role becomes the map key, and each user is appended to the slice stored under that key. The output shows 2 admins, 2 editors, and 1 viewer because the map collected users by their role field. Now let's show the Go-specific best practice. You can append directly to groups at a key even when that key is new. The 0 value is a nil slice, and append handles nil slices correctly. For practice, change the function to return only names grouped by role. That means the result type becomes map string to slice of string. It is a useful variation when an API response should not expose the full user object. This section focuses on merging data with maps. The key interview idea is accumulation. Copy what you have, then add matching values. Map merging is common when 2 systems report counts for the same keys. We copy the first inventory into a fresh result map, then add the second inventory into it. Now we run the code and check that laptop and mouse are summed while unique products stay present. Let's break down the output. Laptop is 4 plus 2, so it becomes 6. Mouse is 10 plus 5. Monitor only exists in the first map, and keyboard only exists in the second map. Now let's show the best production habit. Return a new map when the caller might still need the original inputs unchanged. Mutating one of the input maps is shorter, but it can create surprising side effects. For practice, add a third warehouse. You can either call merge inventory twice or redesign it to accept a slice of maps. The second version is closer to a reusable utility function. Now we switch to numeric slice reasoning. These tasks are less about syntax and more about spotting the simplest invariant. A missing sequence value can often be found without nested loops. For numbers from 1 to n, we know the expected sum, so we add the values we actually received and subtract. Now we run the code with 1, 2, 4, 5, and n equal to 5. Let's break down the math in plain terms. 1 through 5 should be 15, but the slice adds up to 12. The missing value is exactly the gap between those two sums, so the function prints 3. Now let's show the important caveat. This is the best simple solution only when values are unique inside the range and exactly one number is missing. In real code, document that assumption or validate the input before trusting the answer. For practice, solve the same problem with XOR. It is another classic interview approach and it avoids a large sum. After that, decide which version you would explain more clearly under interview pressure. Now we move into array transformations, where small index mistakes can easily break otherwise simple code. Your task is to rotate a slice to the right by k positions. This is useful when a queue, carousel, or schedule needs to shift order without losing any values. We normalize k, split the slice near the end, move the tail to the front, and now we run it to check the result. Let's break down why the result is 4, 5, 1, 2, 3 with k equal to 2. The last two values become the new start of the slice. The modulo step is important because rotating by 7 in a 5-element slice should behave exactly like rotating by 2. Now we show the safer version of this pattern. Because slice rotation often fails on empty input or large k values, always check the length before modulo, then normalize k before calculating indexes. That keeps the function predictable for normal and edge case inputs. For practice, change the input to k equals 7 and predict the output before running it. Then try rotating an empty slice and a 1-element slice. These cases tell you whether your index logic is really safe. Next, we parse a compact settings string, a common interview task because it mixes strings, validation, and maps. Your task is to turn a compact settings string into a map. This kind of parser is handy for feature flags, simple CLI options, and small config values. We split the input into pairs, validate each pair before reading indexes, and now we run it with one valid string and one malformed string. Let's break down the parser. The semicolon separates settings, splitten separates only the first equal sign, and trim space removes extra formatting noise. The key detail is that we check the length of parts before using parts 0 and parts 1. Now we show the best practice for small text parsers. Validate first, then assign. This is better because real input is messy and a parser should fail with a useful error instead of crashing the program. Use split n when only the first separator matters. For practice, change the parser to allow empty values like debug equals empty string, but still reject an empty key. Then add one more invalid case where the input starts with equals. This forces you to separate key validation from value validation. Now we start using goroutines and channels, focusing on a pattern that is small enough to understand but useful in real programs. Your task is to run 3 independent jobs concurrently and collect their results. This is the same basic shape as calling several APIs or processing several files at once. We start 3 goroutines, send typed results into one channel, receive exactly 3 times, and now we run it. Let's break down the concurrency flow. Each job runs independently, but main still controls how many results it expects. The sort is only for stable lesson output. The channel receive order depends on which job finishes first. Now we show the best practice for this pattern. Make the receive strategy explicit. If you know the number of jobs, receive that many results. If the number is dynamic, use a coordinator to close the channel after all workers finish. For practice, add a 4th job with its own delay and increase the receive count to 4. Then try storing a duration field in job result and print how long each job took. That makes the concurrent behavior easier to see. Next, we look at shared state, where concurrent code can become incorrect unless we protect the critical section. Your task is to increment a shared counter from 100 goroutines. This is a realistic pattern for counting completed jobs or successful requests across workers. We use a wait group to wait for everyone, lock only around the increment, and now we run it to confirm the final count. Let's break down the important part. Incrementing a number is not one tiny magic operation. It reads the old value, adds 1, and writes the new value. The mutex makes that sequence exclusive, so 2 goroutines do not overwrite each other's updates. Now we show the best practice for mutex code. Keep the locked section small. Lock only around the shared counter update, not around unrelated work. This reduces waiting and makes the protected data easier to reason about. For practice, add a second shared value like total processed and protect it with the same mutex. Then try removing the lock and run the program with the race detector on your machine. That comparison makes the risk very concrete. Finally, we build a small worker pool, one of the most practical concurrency patterns for controlling parallel work. Your task is to process 5 integer jobs with 3 workers. Worker pools are useful when you want parallel work, but you do not want unlimited goroutines. We create a jobs channel, a results channel, start 3 workers, close jobs after sending all work, and now we run it. Let's break down the channel lifecycle. Workers keep reading jobs until the jobs channel is closed. The results channel is closed only after the wait group confirms that every worker has returned, so the range loop over results can finish cleanly. Now we show the best practice for worker pools. The sender closes the jobs channel, and a coordinator closes the results channel. This is better because workers should not guess whether more jobs will arrive. The code stays predictable even when you change the number of jobs or workers. For practice, change the pool to process 10 jobs with only 2 workers. Then add a small sleep inside the worker to simulate real work. You should still get every result once, even though the processing order may vary. That is all 15 Go challenges solved step by step. If this helped you practice, like the video, subscribe to Dev Level Up, and write in the comments what Go topic or challenge set you want next.